All right, let's talk about background jobs. They're the silent workhorses of our applications. We dispatch a task, it runs behind the scenes, and everything just kind of works. Or at least that's the illusion, right? But what happens when that illusion completely shatters under real-world pressure? So today, we're going to pull back that curtain and design a system that doesn't just work on a good day, but one that truly holds up when things get tough.
I want you to just picture this for a second. Your user is locked out. They are desperately hitting refresh, waiting for that password reset email. But that email, probably the most critical, time-sensitive task you have, is totally stuck. It's sitting in line, waiting, behind some massive job like compressing a brand new 90-second YouTube video somebody just uploaded. Your user is getting more and more frustrated, and your system's reputation is taking a hit. This isn't some hypothetical nightmare scenario. It's a symptom of a much, much deeper problem.
So yeah, how did we get here? How does something that's supposed to make our app faster and more responsive end up causing these, well, catastrophic bottlenecks? The answer isn't usually where we look first. We blame the framework, we blame the server, maybe a buggy library. But the real issue, it's way more fundamental than that.
That's it right there. These meltdowns are almost never the fault of the tools we're using. They are failures in our design. They're the result of decisions we didn't actively make, so our system just defaulted to the worst possible option. And we're going to fix that starting right now by changing how we even think about this whole process. Okay, so the very first and honestly the most important step here is a mental shift. We tend to think of our job queues as just a simple to-do list. Tasks get added, they get checked off one by one, but that's exactly where the fragility comes from. We need a much, much more robust model.
So let's move from that fragile to-do list to this idea of a work contract. A work contract is a durable, completely self-contained set of instructions. Think about it. It gets dispatched into a system where it might run in 30 seconds or it might run in 3 hours. It has to be able to survive server restarts, network failures, you name it. And this is the crucial part. It has to assume that the part of the application that created it is long gone. It's on its own.
And this is what's so interesting when you lay it out like this. The to-do list mentality is just so fragile. It assumes everything is perfect, that the world hasn't changed since the job was created. But the work contract, it's built for reality. It's resilient precisely because it assumes nothing. And once you make this one shift in your thinking, all of the other design decisions we're about to talk about just start to feel completely obvious.
So, with that new mental model locked in, we can zoom in a bit and look at the blueprint for a single, perfect job. This is where we can avoid the two most common and honestly most critical mistakes people make.
Okay, mistake number one, and you see this all the time. Passing a full data object, like a user model or in this case a media model, directly to the job. I get it, it seems convenient, but it's a trap. By the time that job finally runs, the data inside that serialized object could be completely stale. The video's status might have changed, or maybe the user who uploaded it was deleted. The right way? It's so simple. Just pass a primitive ID. The job's first responsibility is then to fetch the absolute latest version of that data from the database right before it starts its work. No more stale data.
And that first principle, just passing an ID, leads us right into our second big rule, the single responsibility principle. We hear about this all the time for classes, but it is absolutely vital for background jobs. A job that tries to do everything is basically guaranteed to fail in the most unpredictable and frustrating ways.
Let's go back to our YouTube video example. So a single do-it-all job might try to compress the video, then update its status in our database, then send a notification to the user, and then sync some metadata to the YouTube API. Now, what happens if that very last step, the API sync, fails? Well, the entire job retries from the beginning. That means you are recompressing that massive video, an incredibly expensive operation, all because you're trying to retry a simple API call. The solution is obvious. Break this up into a chain of small, single-purpose jobs.
Okay, so we've perfected our individual jobs. You can think of them like our cars. Now, let's zoom out and design the roads they're going to drive on. We have to stop thinking of our queue system as a single-country road and start seeing it as a proper multi-lane highway system.
Seriously, using a single default queue for everything is the design equivalent of building a major city with only one road. Yeah, it works for a little while, but then it just doesn't. The moment a slow, heavy truck, like our big video compression job, gets on that road, everything grinds to a halt for the fast sports cars, like our password resets.
So, the crucial takeaway here is to design a queue topology before
an outage forces you to. This is a brilliant, practical setup. You've got a critical queue for things that absolutely, positively cannot wait. Then there's a dedicated media queue for those heavy, long-running video jobs, keeping them out of the way. And you isolate sync jobs, so if some third-party API goes down, it doesn't take your entire system with it. Each lane has a purpose, it's organized traffic. So we've designed our jobs, we've designed our infrastructure, but things are still going to fail. It's just inevitable. Professional, resilient systems aren't built on the hope that things won't fail. They're built on the absolute certainty that they will, and they plan for it.
A one-size-fits-all retry strategy is just as bad as a one-size-fits-all queue. I mean, think about it. A brief network blip is a totally different kind of failure than someone entering an invalid credit card number. Our system has to be smart enough to tell the difference.
So how do we apply that intelligence? Well, for transient failures, like that network blip, we just retry quickly a couple of times. For an API that's rate limiting us, we need to be smarter. We back off exponentially, giving it time to recover. And for a permanent failure, like that bad credit card, we stop immediately. Retrying is pointless. It's just going to waste resources. We fail fast, and we alert a human.
All right, let's talk about one of the most dangerous failure scenarios out there. Your job is halfway through writing a new compressed version of a video file to disk, and then, suddenly, the process crashes. The server reboots. What state is that file in right now?
If you were writing directly over the original file, you're now left with a corrupted, totally useless file. The only safe way to do this is the write, then rename pattern. You do all your hard work on a temporary file. The original is never touched. Only when that new file is complete and you've verified it, do you perform the final magic step, an atomic rename. This is an operation that's guaranteed by the operating system to either succeed completely, instantly, or not at all. There is no in-between corrupted state. It's foolproof. Wow. Okay, we have covered a ton of ground, from high-level mindsets all the way down to low-level file operations. So let's bring it all together into a simple, actionable checklist you can use before you ship your next background job.
All right, this is your pre-flight check. Let's run through it. First is your queue topology, your highway system. Actually defined? Does every single job take a simple ID, not a stale object? For every job, have you explicitly set its retry, timeout, and backoff strategy? No defaults? Does it have a good failed method so you know exactly what went wrong when it does? Is that timeout value a generous safety net, not a ticking time bomb? And what about bulk jobs? Are you chunking them to avoid blowing up your memory? And do you have a dry run to test things first? And finally, if your job writes a file, is it using that critical write then rename pattern? Think of this as the absolute bedrock of a system that's built to last.
So, I want you to go take a hard look at your own systems. Are you treating your queues like a fragile to-do list, or are you designing them with resilient, self-contained work contracts? Because honestly, the difference is everything. Is your system's background work actually built to last, or is it just the next big outage waiting to happen?